Maintenant, nous allons explorer.
Now it's time for us to explore the challenges and opportunities concerning the scaling of quantum technologies for practical use. And we're lucky enough to have with us experts who are highly renowned. Our moderator for this panel is Dr. Celia Merzbacher, and there will be Ms. Katie Pizzolato, Dr. Krista Svore, Dr. Rajeeb Hezra, Dr. Gregoire Ribordy, Dr. Alexander Ling, and Dr. Takuya Kitagawa. Thank you.
Thank you so much. And as the panel comes up, I'll just welcome everyone here. Thank you for staying until the end of today's program. And I can't think of a better, go ahead and sit anywhere. We don't have assigned seating here. I can't think of a better talk to follow than Bill Phillips' talk that we just heard. He really set the stage for us and introduced some of the concepts that this panel is going to build upon. So this is the panel from the industry perspective. And as Bill mentioned, I am Executive Director of the Quantum Economic Development Consortium, which is a consortium of stakeholders that brings together representatives from the whole community, the whole ecosystem. But we're really industry-driven, and our mission is to enable and grow the quantum industry. It's not the quantum computing industry alone, and it's really a global effort, as he mentioned. We welcome members from around the world today. So you can find out more about QED-C on our website. Industry is building on something that was, I think, mentioned in one of the panels this morning, what takes physics from the lab to the real world. And that's really why I thought it was important to have this panel today. The International Year of Quantum, which we keep saying IYQ, and we sort of stop after quantum, but I think up here on the screen it says quantum science and technology. And we're going to be talking more about the technology on this panel. It's not just about the science, and industry is how science gets out of the lab and into practical applications. Why now? We've been hearing from several speakers about the rich history and that we're celebrating 100 years since some milestone was made. And we're really building on 100 years of theory and physics and even experiment, which has gotten more and more refined. But as Bill Phillips showed with his movie, Moving Atoms One by One, this is building also on our ability to control matter at that scale of atoms and molecules, individual atoms and molecules. And that's sort of the whole field of nanoscale science and technology. So we're building on what's been going on now for several decades to allow us to do practical things with our understanding of quantum behavior and properties. And I will add to Anne's talk this morning by mentioning that there was a Nobel Prize given in 1986 to the inventors of the scanning tunneling microscope, which was really the first implementation of this ability to touch and feel individual atoms. That was work done at IBM. So the applications of quantum, we've also heard referenced. There's a lot of focus on quantum computing. But there are also applications in other fields, and we're going to be hearing about some of those: quantum sensing, quantum networking, and communications and security, among others. Quantum technology it has to solve a problem for a business to be able to generate revenue. And that means it has to do something better than the current way that it's done, or it has to enable something new that we can't do at all today. And so that's a really important thing from a business point of view. And we've heard and talked a little bit earlier today about achieving societal benefits and tackling the hard SDGs, the sustainable goals of the UN. But really, in order to do all of that, businesses have to be able to make something that's useful and that somebody's willing to pay for. And then it will spill over and be taken up by all the other users of the technology. That's just normally how things work. So the commercially available tools, I'm sure, are going to help to address the challenges that we're all interested in. And finally, and then I'll open up the questions for the panel, achieving quantum technology's potential requires, as we've heard, and we heard a whole panel on this, quantum qualified or quantum prepared or quantum ready workers. Spending a lot of money by government on quantum research is going to produce nothing if we don't have people to do the research and to build the companies and make it real. So that's another important aspect of what this year of quantum is about. It's about raising awareness and getting people excited about it. And so I think everybody here is already on board. We're preaching to the choir in a way, but our job going away from this meeting is to carry that out into the world and help spread this message. So with that, I will allow the panelists to introduce themselves. They'll do a better job than I would. I will just sort of quickly run down the, we'll start at that end. We have Gregoire Ribordy, who's co-founder and CEO of ID Quantique, a Swiss company. Let me just run down and then we'll come back to you to sort of say how you fit into the ecosystem. We have Takuya, sorry, Kitagawa-san. Oh, that's you. Yeah, sorry, you can tell. We met once on the small screens. Alexander, right? Alexander Ling, who's a principal investigator at the Center for Quantum Technologies and associate professor at the Department of Physics on the Faculty of Science at the National University of Singapore. And he's co-founder of two companies, Spectral and S15 Instruments. Next, we have Katie Pizzolato with IBM. She's Vice President of Quantum Algorithms and Scientific Partnerships. I'm very interested to hear from you, Katie. Then we have Krista Svore with Microsoft, where she is Principal Research Manager of the Microsoft Quantum team. Then we have Takuya Kitagawa, President of QuEra Computing, which is a spin-out from Harvard and MIT, and the work that actually I think was referenced in the previous talk. They use neutral atoms to do their quantum computing. And then finally we have Rajeeb, or Raj Hezra, CEO of Quantinuum, which uses trapped ion qubits to do quantum computing, previously with the semiconductor industry. So we have a very kind of broad set of backgrounds and expertises. So my first question, I guess, to each of you, and I will point out there was a comment made in an earlier panel about the lack of diversity on this panel. Most of these companies, but not all, are US companies. So we have a Swiss company and a Singapore company representative, and we have diverse technologies being used by all of the people on the stage. So we look forward to kind of hearing from all of your perspectives. So I'll start with Gregoire. Briefly, how do you and your organization fit into the quantum industry? If you could just share with us a little bit about ID Quantique.
Yeah. Good afternoon, everyone. Thank you, Celia, for the introduction. So we're a Swiss company, and I'm proud to represent Europe on this panel. And so the company is pretty old, actually. It was founded 24 years ago, so almost a quarter of a century, which, you know, when we celebrate a century of quantum, you know, it's a long duration. I did a PhD in quantum physics and felt that doing research was very hard, and I wanted to do something simpler. So I started a company in quantum in 2001. Little did I know. So what the vision was to bring QKD technology, which was where there were prototypes at the time, to bring this technology to the market, to enable quantum communication, a first generation of quantum communication, to ensure long-term security of information based on physics and not computational security. And so at the time, that's something we still do. At the time, we had to pay bills and salaries, so we had to find something else, some other products. We sold also single photon detectors, tools for people working with single photons, and that's how the company really started and allowed us to reach where we are now.
So selling picks and shovels at the beginning. And I will tell you all to check out the podcast that we did last year. Been there, done that. QED-C has a podcast. Next.
Okay, so I'm going to be a bit of a spoiler in the panel. So I'm not here going to represent any company, but I'll wear my academic hat. So I come from the Center for Quantum Technologies in Singapore, which is a basic academic research center. And our task is actually to form students through exposure to basic research. But having said that, we actually work very closely with industry. We work very closely with the Singapore government to grow the industrial ecosystem. And CQT actually runs quite a number of translation programs in Singapore. We oversee programs for quantum communication networks, quantum computing software development, and we are heavily involved in the quantum foundry efforts in Singapore as well. And also, a lot of the startups that we have in Singapore, including my own startups, of course, they're all very closely linked to CQT. Right? And just briefly to switch hats again to my industry hat, when we started the two companies, S15 and Spectral, S15 was looking more at providing high-quality instrumentation that had been developed within the center. And we were getting a lot of requests from collaborators asking for a lot of these instruments, and we could not meet them on an academic basis, and that's when it spun off into a company. And for Spectral, it was actually an offshoot of our own research into building entanglement networks, global entanglement networks. And the students and postdocs working there saw an opportunity to actually take the IP out of the university and try and build this global network. And so this is the background of those two companies.
A great example of getting physics out of the lab and into the real world. Kate.
Hi, thanks for having me. I do like your bet idea, by the way. I think we should all take bets on that. I'm Katie, I'm from IBM. IBM has really been pioneering quantum computing for quite some time. Over multiple decades, early days of quantum information theory, lots of the groundwork for all the codes that we're all talking about and implementing in error correction. We put the first quantum computer on the cloud in 2016. We have lots of efforts about democratization of the technology, bringing the workforce to bear, and really just bringing practical quantum computing to life. I like going at the end of the day too, because you all have said a lot of good things that you might hear me repeat today, because a lot of people have made great points on this point today.
Yeah, good evening, bonsoir. I'm Krista Svore from Microsoft, and at Microsoft our focus is around quantum computing. We're really working across both software and hardware, so Microsoft is a quantum hardware company and a quantum software company. We have built out a platform for quantum computing. Our focus is to really bring reliable quantum computing, right? Quantum computing that can be used for practical applications to our customers, to people, to scientists, to young people as well, all around the world globally. So we have a platform for quantum computing, we have services there, and we really want to ensure that people are using quantum computers with the other technologies, right? When we think about quantum technology and quantum science, right, it's using that with your classical computing, as we call it, right? Your digital computing, your AI, right? Not something that just replaces it. So our focus is building out a platform to make that possible, to make it easy for the integration with AI, with high-performance compute, with cloud compute, and to bring real applications to life, to make it practical.
Hi, my name is Takuya from QuEra Computing. QuEra builds and develops quantum computers based on cold atom system. So Professor Bill Phillips showed our movie for how our quantum computer works. And we are making good progress in quantum technology, especially quantum error correction. We have published, for example, in 2023, demonstrating 48 logical qubits. And at the end of last year, we also demonstrated something called magic state distillation, which is a critical component of doing a quantum computer in the future. We've been providing the access to our analog quantum computer from 2022, and this year we are planning to install our second generation gate-based quantum computer in Japan, in ICE. So right now already, technology is here, and people can have access to our quantum computer. So that's how we are relevant to the society.
And how big is QuEra?
QuEra is still, it is about 70 people team right now, and it is based on Boston because it came out of Harvard MIT.
So thank you, and good afternoon to everybody, and good afternoon to everybody on the panel as well. My name is Rajeeb Hezra. I am the CEO and president of Quantinuum. We have one singular focus across the 500 people in our company today. We build the world's best quantum computers in order to go solve some of the greatest challenges of humanity as quickly as possible. We're a full stack company. We work on both hardware and software. We've been in existence as Quantinuum from November 2021, but our history goes back well before that in software and hardware companies separately, and Honeywell on the hardware side and Cambridge Quantum on the software side. And it's a real pleasure here to be seeing all the different opinions, but the great convergence to one question, which is, what does the quantum future look like, and what can we each do to play a part in it and to accelerate it?
And I think there's so much abundance is why you're, able to, why my organization has been successful at building a community, because there are some common needs, there's a lot of hard work to be done, but I think we can get a sense of the breadth of what's going on in this space. I'll sort of start back with you, Raj. So we are focusing, I think, mainly on quantum computing, just the nature of this panel, not altogether, but even if you open it up and say there are applications in other areas, which applications are you particularly excited about when you think about quantum, and why?
That's a great question, and I'm glad you said which ones I'm excited about versus which ones we think is the winner. They're two different questions. I would contend that there's really no credible answer to the second one, but there are good hypotheses to many on the first one. We believe, first, before I answer your question, we believe quantum computing is not a replacement for classical computing. So when I answer and say these are the applications we think are very interesting at different time scales, it's not about quantum computing replacing classical, but the combination doing something that would not have been either possible with classical computing, even as the advances are getting made, it's not about just making sure that the old is done in a new sort of way, although that will happen in places. The kind of things we are really interested in is, as we announced today, where does quantum computing give humanity's ability to see and manage and predict and modify the way things are with information that we wouldn't have had otherwise? So we are a great believer that AI and artificial intelligence and generative AI has arrived at the right time, but it needs new glasses. And those new glasses is quantum computing that allows you to see the world that is governed not by the laws of the Newtonian mechanics, but quantum mechanics. And it now it will be able to look at things that we've only dimly or grossly estimated, and be able to now get far closer to reality, thereby letting things like generative AI not be just a occasional use or a recreational use to write letters and other kinds of things, but really solve problems like how do you deliver drugs in particular things like metal organic frameworks, and that have the absolute safety as well as the efficacy of a delayed delivery of a drug, or personalized medicine. It's those kinds of things that I think I'm very excited about, where quantum is a unique both computational element as well as a data generator for the natural forces by which we are taking human ingenuity forward through computing.
So what I heard you say, and I'll see if you agree with this, is that quantum computing is likely to be hybridized in some sense with other technologies, both classical computing, so classical plus quantum, and plus or minus AI on top of all that.
Yeah, what I said precisely is the computing infrastructure is going to be both classical and quantum from a hardware sense. At the infrastructure level, software will make it easy to go between them. Just like, 30 years ago, there were no GPUs. And computing infrastructure software said, okay, we can make it run on the CPUs that you have. Then came virtualization, and people said, okay, well, the machine's kind of virtual, we'll move it around. Then came GPUs, you added it to CPUs, and now you had a hybrid infrastructure. We're taking that and extending by many folds by saying now you're going to execute workflows on a hybrid classical plus computing infrastructure. And now we don't talk about a single application, we talk about a workflow, in which case there are many applications interacting with each other, helping each other, versus replacing the other totally.
Yeah, and so I'd like others to sort of add to that. I think this is an important point. People sometimes are so focused on just one type of quantum computer as the answer, and that's probably not where we'll be in the, at least near term. Kate?
Yeah, and I think maybe keying off a bit of what you said about the introduction of GPUs, like the thing that really brought GPUs to life, not only from the gaming beginning, but where they are today, was the discovery of new algorithms running on that technology. And now that we have this quantum technology, I think what we're all excited about is really what we don't know about yet, right? We have the ideas, we have the theoretical principles, especially in chemistry and materials and things like that, which I think from a human point of view, we have lots of hope in how they could solve our daily problems. But I think it all comes down, to me, what I'm most excited about is what I don't know about and how quickly that can turn with all the smart people that everyone's bringing together, thinking about how to use this technology. And, I think we'll have to make bets, but I think we'll also have to arm wrestle on who has the best quantum computers.
I'll add a few comments here, just building on what's already been shared. I think I've worked on quantum algorithms. What do you do with a quantum computer? How do you program it for a long time? And in the early days, we thought, okay, we need the answer from the quantum computer, right? And we thought of it really more standalone. And this is where this evolution, I think, with the explosion, of multiple technologies, right? Cloud computing, right? 10 years back, it wasn't obviously where it was today, right? 15 years back, 20 years back, we didn't have the cloud. We didn't have that level of compute and that access in your pocket, right? Now the explosion of AI, right? You have the ability to speak in your natural language, program in your natural language, right? That, in addition to using AI for science, is incredibly powerful. And so now we can think about the quantum computer, as Raj mentioned, right, as this way to produce information that we don't have access to efficiently anywhere else in the, in the universe, if you will, right, on this planet. And so using now this information, even a small amount of really accurate information is powerful. And we can now use that in conjunction with the AI models we are already training, using, building up, whether they're for science or other applications. But of course, today we're focused on science and technology, right? Think about AI for physics, AI for chemistry, AI for medicine, AI for health, right? And mixing in new information that you cannot access otherwise in any efficient way, right? Getting that from a quantum computer. So we used to think about the quantum computer as the answer. Now we think of the quantum computer as a provider of information that augments on top of the other capabilities that governments, regions, institutes, companies are invested in, right? So it's really not a replacement. And building further on what Katie just said, right? What's so exciting is we now are entering an era where we have machines that can give reliable information. Logical qubits, reliable quantum computing. You now get information that is reliable, and you get to try it, right? We have been up against a very large hurdle in quantum computing. We have had to prove something mathematically, that it's better mathematically, right? That's hard. We don't get to show it with a heuristic against a standing baseline that we ran on the machine yesterday, right? But now we're entering that era. That's where I think the International Year of Quantum being 2025, it's so pivotal, because this year we will be running new solutions. We'll be getting new information from the machine that leads us down this path of more predictive capabilities, first time right prediction, the ability to model before you synthesize and actually get the recipe out, right? These are amazing capabilities. So I think it's a real transformation. I'm really excited to see, what information do people want from a reliable quantum computer?
I'm going to let Takuya, and then I'm going to get down to the non-quantum computer people.
Thank you. I very much agree with what Krista just described. If I may step back a little bit, what excites me is really this possibility that quantum computer can simulate quantum mechanics in nature. That's all the our panelists actually discussed prior to this session. And because of this, we can transform experimental science into computational science. That's a computational paradigm shift we are going to observe. So once we have enough scalable quantum computer, scientists can reduce the amount of time they have to spend in a wet lab doing a very challenging experiments, and instead spend time on the computers to reduce the number of possibility and do more much faster work that would dramatically increase the rate of scientific discovery. So sometimes I make a joking statement. There are so many Nobel Prize winners in this room, but I sometimes make a joke that Nobel Prize is a once a year event, but once quantum computer comes in, maybe it becomes once in 5 minutes event. And that's the kind of excitement of a dramatic acceleration of science is waiting for us. And there are many fundamental science problems that we would love to solve. Like, for example, finding a new catalyst that transforms CO2 in the air into solid form or liquid form, or finding a higher efficiency solar panel, etc. So I think that's a way I would phrase maybe what Krista was explaining just now.
Thank you. Gregoire.
Yeah, from a quantum communication point of view, what I find exciting now is that the technology is ready for prime time. There's been a lot of progress recently, and I'll mention just two examples. First, quantum random number generation, which are very simple devices, use quantum superposition to produce randomness, zeros and ones, and that's something difficult, or you could say impossible to do with a classical computer. But if you talk to cryptographers, they all know that you need good random numbers for applications such as cryptography and many other applications. And I'm going to show you here a little card, and you'll see nothing, and that's what's exciting, because on this business card, there are two little black dots, and these are chips, and these chips are quantum random number generators that are installed in mobile phones, and there are millions of mobile phones that are equipped with this quantum random number generator. So it means that the technology is ready and mature for broad, so for mass scale applications. And another development being in the field of quantum communication, QKD allows to distribute encryption keys. We've heard about the principle, and guarantees long-term security. And so there's been some adoption of QKD already. The first customer that used QKD from our company for serious applications, so I mean not a university playing with it, but a security department, was in 2007. So it's been a long time, and following that, there's been gradual adoption. But one of the big barriers was always the certification of the technology. Somehow, if you buy a QKD system, you're not a quantum physicist. You can trust me, but it's even better if someone who understands the technology verifies it for you. And just a couple of weeks ago, we were able to announce the fact that our QKD system is now certified. There's one country that has certified this system. And so it's a big step. It will make adoption of QKD technology much easier for a lot of users. And here, I think there's a theme with quantum computing. We heard that quantum computing will not replace, we'll have a hybrid model. It's going to be the same with quantum safe security. There was an initial fight between physicists and cryptographers, who would win the war. I think the solution is actually combining QKD and PQC. There will be PQC everywhere, that's for sure. It may take a bit of time. We heard the call this morning for prompt action, but PQC will be used everywhere. But QKD will also play a role in critical links, critical infrastructure, where you need really long-term security. And that's a strategy called defense in depth that users in the financial sector, government, and this kind of industries are already adopting today. So it's a very exciting time for quantum communications.
Right. So I have two technologies I'm really excited about, and the first one is in quantum communications. And just to echo what Gregoire said, definitely in quantum communications, when we move into this transition of a quantum safe future, right, we're going to have PQC and we're going to have QKD. And one of the biggest things we're going to have to work out is where do we apply them correctly, right? Because each of them have their own strengths, they also have their own drawbacks, and we need to understand how to do them efficiently so that we can actually have the best quantum safe communications in the future. And beyond that, I also see that there's a way to also move quantum communications for quantum safe security on a global scale. for example, using satellites. And this is something that more and more countries are starting to pursue. Our friends in China are, of course, the first ones to actually demonstrate that. But I think many other countries would be interested in seeing such a technology as well. Now, the second technology I think is actually pretty interesting. I want to wave its flag here, is quantum sensing, right? Personally, we already heard about the gravimeter that is on the volcano collecting data. And that's actually one of the technologies I want to talk about. We built a similar technology in Singapore, and we deployed it to actually calibrate classical gravimeters. They are much more smaller and portable, but they drift very often. So the idea is that these classical gravimeters will always come back to the quantum gravimeter to be recalibrated before being redeployed for survey. And this is a strategy that Singapore has actually tried out in 2 different locations to understand underground formations with the idea that perhaps we can actually identify sources of geothermal energy. And this is something that has generated data that we are looking at and could be deployed to many other parts of the world as well to help for mining or mineral search and exploration. So I think quantum sensing is also a very exciting technology that we're looking at.
Yeah, I think it's important for people, and I know we have a lot of real experts in the room, but there also is a diverse audience here. There are a lot of different kinds of sensors. We heard about ones for imaging in biomedicine, but there also are these applications out in the field, and if you include measuring time as a quantum technology, which I think it is, then these super accurate clocks are another really important type of device that's already available today. So the quantum-ready workforce, as I mentioned, sort of still needs to be developed. And it would be, I think, really interesting for people to hear from you. You're in the business of hiring people. What kind of skills would you like for the people who are out there educating the future workforce to instill in the students that they're teaching? What would you want to say to students who are thinking, oh, what should I be sure and take so that I'm preparing myself for this opportunity in the future, perhaps? And maybe you can sort of give a sense of how challenging it is to find qualified people. Is there a shortage? Is there a gap right now? So anybody you want to start with?
Right, is it back on? Yes. Yeah, so just recently at Microsoft, we announced a new program called the Quantum Ready program, which speaks to this, Celia. And this is really geared more towards industry and folks in jobs today, right? Let's say that really offers an understanding of the application space. For example, how would you bring this together with AI, with cloud compute, with high performance computing? Speaks to different industry opportunities, areas where quantum computing in particular can advance your capabilities. And so, encourage everyone to look at the Quantum Ready program. But let me also speak to for younger people. Right. I think, there's a huge opportunity, to train the trainer, right? I think, there's one level of work we need to do globally that really helps teachers, professors, right? Those that are interacting with the younger generations learn about quantum mechanics, how it applies, how is it happening in your everyday life, right, to inspire a younger generation, but also how will quantum computing impact areas of science, right, and start teaching and sharing on that. And then also, for younger people, I think, of course, at the core, we talk a lot about quantum skilling, but at the core, it's math and it's science. Right? And so continuing to ensure that our young generations, our younger people, are learning the foundational mathematical and scientific capabilities, that's at the core, right? I myself, I never took quantum mechanics until graduate school. I was a math major, right? I learned about quantum computing in a course on cryptography, right, from Andrew Wiles, a Fields medalist, right? And I learned about it because I learned about Shor's algorithm. This was just maybe a couple years after Shor's algorithm. I learned about a machine, a potential computer that could break factoring, break RSA, the mainstay of e-commerce today. And I was fascinated that there was another type of computer, right, which at that time, right, we didn't have a quantum computer. There was another type of computer that could totally overturn what I thought computation was and what it meant to compute and what the definition of computer was, right? And so I think, these avenues, right, understanding how quantum mechanics, quantum science, quantum technologies, whether it's sensing, computing, right, really reaching cross-disciplinary, and across the domains, it's so important, right? And it's the core of mathematics and science, right? Those foundations that also are so critical. It doesn't have to just be quantum mechanics, right, to have a quantum impact.
Yeah, I think keying off of what you said as well is that, like, similar to our accelerator program where you're thinking about how do you really work on those problems, and if you think about the types of people you're working with in industry or whatever it is, like, there's all a similar persona. There's a lot of people out there who spent time in these kind of degrees within their academic environment, and if they didn't want to come out and do something from a research perspective and they came to industry, 5+ years ago, you just went into a normal kind of classical environment. So I think what we need is a lot of those people to raise their hands and say, I'm interested in this, I have a vested interest because I know enough about the technology to inform my stakeholders around me, whether from an industry perspective, but be willing to just kind of jump in. Everyone can get started today. We have lots of learning platforms available. There's really not a large barrier to entry to getting started, and I think that everyone should think about getting started. I also really think what's important, and I see some transition in, is exactly that, like getting out of the quantum native environments in the academic universities, and like what are engineers going to use quantum computing for, and how do we start thinking about those that are going to apply the technology instead of just teaching about the technology. And I see the change, but when you look at the roadmaps that we have, and we look at what the types of computers that are going to be available within the next 3 to 5 years, we are behind on the workforce that can use that. So I think raise your hand if you know something about it and you're interested, because I think every industry it's hard to find people. Every industry is looking for someone, and I think a lot of those people exist within those organizations already. And I think get started from wherever you are. There's tons of information out there.
Yeah, definitely, interdisciplinary skill set is very important. Maybe going back to, Rajeeb's point and, Krista's point, the key is use quantum computer as a simulator of nature and make AI learn, classical AI learn the process. Because if you look back how, classical AI evolved in the last couple of years, the first example was AlphaGo, right? So when AlphaGo was learning from previous play of professional players, the growth was, okay, it was good, but okay. But once they started learning from simulator of Go, it dramatically, improved its performance. So in a similar fashion, as soon as you have a simulator of the process, classical AI is extremely good at learning it. And quantum computer provides one of the best, way to, simulate the nature. And what that means is you have to actually, the people with the AI skill and the quantum computer skill will be in much demand in the next 3 years. And with hundreds of billions of dollars investment coming into AI, this is going to be double acceleration of the field itself, right? AI, but also quantum computer will evolve together. So I would think that time scale of this kind of era coming in is going to be much earlier. So pay attention to this. Interdisciplinary skills will be a very important thing.
Yeah, just going back to one point, I think to answer your question very directly, the workforce is going to be the key limiter to how quickly we can take quantum technologies forward. And I don't mean I'm going to sit here and lament that not enough people are interested in mathematics or physics or chemistry. It is a question of awareness-driven inspiration, right? And I think some of it we just have to suffer through. Because that was true in the early days of computers, right? I mean, the people who built the computers were the people who used them, because you had to know things like, ASCII codes and write machine language in order to add 2 + 2, right? But what we have to do is sit here and think about the road ahead, and I think I'll pick up on something Krista said on multidisciplinary, right? If we again, what we've learned from history is if we go back to this paradigm of people who build and people who use, we will be stuck. What we have to do is get the people who use to be into the tent way earlier, not trying to speak the lingua franca of people who are building things, but speak their own lingua franca and together co-design a solution. Today's if you look at where coding is, right? I have 2 kids and I see their friends. They actually don't know what computer they're running on. They cannot answer a question about the architecture of the machine, but they know what problem they're trying to solve and what kind of computing resources they need. That's the holy grail, right? Is a multidisciplinary approach with a mindset and a culture that says, I have a set of tools. How am I going to solve an important problem that has value? And I think for that, we have to focus on building that early on, encouraging and being inspiring, right? Today, quantum computing, quantum technologies, frankly, is daunting, right? It has this aura of only really smart people get it, which may be actually true, but it has to be democratized and mentally made accessible that I can aspire to have a career in it. I can aspire to make a difference in the world by going into this field. And it has to kind of come from success begets success, opening doors, having multidisciplinary efforts going on, and not just at those that are graduating with PhDs, but kids who come into museums. I mean, and see things and go, why? Their innate curiosity is fueled by, how did that happen, Mom and Dad? And they're told.
I think this IYQ is going to help add to that conversation. Did one of you want to?
Yeah. So I completely agree with the previous speakers about multidisciplinarity of quantum. When you build a QKD system, you start with a QKD protocol. You build some photonics parts, single photon detectors, analog electronics, digital electronics, software, etc. So what I find difficult for a company like us is to find engineers that understand enough of quantum mechanics to translate, to build systems and make them work properly. And sometimes you have great surprises. One example is when we were building one of our first QKD systems, as physicists, we knew how to do the physical part, but the post-processing, the signal processing was more difficult. And there's one part where you need to multiply 2 large matrices. And we didn't know how to do that efficiently. We had a software engineer that came from data science, and for him, in 30 seconds, he found a solution, and we're able to solve this problem, which would have taken us a long time. So that's the positive side. Now, QKD, you do single photon communication. One time, one electronic engineer was experimenting, and he found that somehow when you increase the distance, the rate goes down because you don't detect enough photons. And so he thought, I'll increase the signal, I'll send more photons, just to make the system work better, because he didn't grasp that the whole idea was to work at single photon level. So this is to illustrate that I think one of the challenges to get engineers that understand enough of quantum so that they can contribute to the development of products. And right now what we have to do is just train them because there are not so many of these people. Now there's a second category, and in a science conference it may not be what people think about, but it's people doing sales and marketing. Translating the value of quantum into words, into that users, that customers can understand is very difficult. And I think that's an area, I would say, if someone is interested in coming and wants to make a difference, I would encourage to getting a dual training in sales and marketing, but also quantum in order to, because there'll be a lot of future for this kind of people.
Yeah, I think my own personal point of view is that we really need to be a multidisciplinary team. But there's always a big challenge. Because when you build a system, you're going to need systems engineers, software engineers, electrical engineers. And they need to be very good at what they do. You don't want to have a half-baked engineer coming to the team, knowing some of electrical stuff, some quantum stuff, not good at either one. That doesn't work. So I think one of the big challenges, of course, is how to actually develop the management skills to actually, bring in people of different disciplinary backgrounds and then manage them well, and also to give them the correct amount of training so that what they're doing, they understand what's happening there. And the people with the quantum background, they would actually have to provide, they'll have to be like the system architects to actually lay out very clearly what has to be done. I think this is something that the space industry is actually kind of good at. This is something I learned when I started to work on satellite projects, that there are very clear ways of communicating to the different sub-teams. This is something that as we build more and more complex quantum systems, we want to take a leaf from what they do over there. And just to echo your point about lots of resources out there. Yeah, I think if you are very good at your own discipline, you want to contribute to quantum, have a look at what are resources online. Just to plug what we do in Singapore, we have something called the Q Talent Program, where you can go online and take bite-sized courses about different kinds of quantum concepts, and that will actually help you to understand a little bit better how the technologies work and the fundamentals of the science behind those technologies.
Yeah, I think there really are avenues open to everyone. I was at a big conference last week in California. It was for photonic engineers, and they had a sort of workshop on the day before the main event for non-quantum professionals to learn about quantum. So there are professional societies that run these programs. If you're mid-career and you want to upskill, there are programs that are for younger learners. There's really something for everyone. I will also add to this conversation about the skills and the diversity. We did a study where we surveyed the QED-C members and asked them, what jobs are you going to fill? And then for each job that they identified that they expected to hire in the next 3 years or so, we asked, what skills do you want that person to have and what degree would you prefer them to have? And the results were that most of the job descriptions or titles did not say quantum. They said software engineer or circuit designer or something. Most of the skills were not quantum skills. They were very traditional, electrical engineering and so on. And most of the degrees that were preferred were not PhDs in physics. And so there's a huge range of positions and career paths and entry points. And to your point, Gregoire, we did a sort of heat map diagram that showed there were sort of 3 clusters of skills and jobs. And there were the software ones, the hardware ones, and the business ones. And so they were all very important, even when we did the survey now several years ago, and I don't think we would get maybe significantly different results today. Multidisciplinary, someone joked once that the perfect person I want to hire is 1/3 engineer, 1/3 physicist, and 1/3 computer scientist. Those people don't even exist, so you have to be building teams, and it is challenging, I think. Yeah.
Maybe another characteristic, thank you. Another characteristic that's very important is probably first principle thinkers. Right now there's a lot of hypes and could be sometimes disappointment coming from some no-go papers, and it's very important to be excited about the field from your own point of view, and you cannot just rely on other people saying this doesn't work, that doesn't work. You need to be able to form your opinion, and that's the way you can be very cautiously optimistic about the field. So I find it very important to be first principle thinker.
And another thing that I'll point out, you can go find this paper on the QED-C website. There were some skills that were checked only by one company, and there were some skills that were checked by almost every company. And so we did sort of pull out the ones that we called the most important skills. So again, if you're sort of in a student mode and you want to make yourself qualified for as many sort of options as possible that you would want to sort of look, so math and certain, maybe a little Python or whatever and so on, can equip you for a lot of different opportunities in the future. So next question. Many nations are making strategic investments. We're all, I think, seeing that in quantum science and technology, in the research side especially, and more, I think, in trying to help commercialize the results of that research investment. do you have any sort of advice for what this International Year of Quantum and all the organizations that are participating, what could be done perhaps under the IYQ umbrella to connect these efforts and to sort of accelerate progress, especially towards the sustainability goals and some of the global benefits that perhaps we're hoping for?
So maybe I can take a quick start, and I'm sure all of us have opinions on this one. It is true nation states are making strategic investments. It is a good thing that quantum is recognized as part of any national future or strategic advantage. I think the International Year of Quantum has two letters I associate with it. One is collaboration, right? And I understand that for various practical reasons, there's national security interests and other industrial security interests, but I do think at this early stage of development of a core technology or a deep, a deep tech as they call it, it is important to keep lines of communications and collaboration open. So forums that we can form, and I'm not just talking about the experts, even at the student level, student challenges, where people get to see each other's approach to problems, see what is common, see what is unique is very important. I think the other than C, the other one is S, is scrutiny. I think we've scrutiny as in all levels, scrutinizing a little bit more to separate, as you said, what is hype versus reality, right? A little bit more intellectual rigor around trying to separate what is a conjecture versus what is proven. I'm not saying there's not a role for the art of the possible, that everything has to be art of the proven, but the balance has to come in. Because the industry has now been in existence and gone through a little bit of a hype cycle to have generated enough data to be able to have an engine go through it and say, okay, we can separate near reality or reality from this. And that scrutiny goes all the way up. Are we doing the right sort of things that got the industry accelerated to this point that will take us through the next phase of acceleration, right? Is it the most efficient funding structures? Is it the most efficient way, even in financial policy and taxation and incentives that governments are doing? But I again go back to workforce development. The biggest thing that the governments can do, which has been proven for 30 years in HPC and supercomputing, is they form the market. Multi-core, multi-threading would not have existed if the governments hadn't stepped in and said we have large problems that is well ahead of what the industry needs are, but we'll invest in the technology. So investing in the technology with scrutiny on which technologies have the best chances of accelerating and then driving collaboration around that focus, I think is what the International Year of Quantum can really put a spotlight on.
I feel bad. I'm going to say a lot of what you said. But I think the one thing I'd like to add is we spoke a little bit about this at lunch, right? That one of the great things that places like this bring us together is the academic community, the industry community, we're all still very well tied together. So that scrutiny kind of comes by nature, right? I think a lot of the hype and then the scrutiny and the hype and then the discussion, but I think, we all demand of each other that kind of scrutiny to make sure we're doing the right things. And when we all sit up and say, this is why we're excited about something, that we have that scientific rigor behind it. And I couldn't agree with you more on awareness. I think that if the more people we get from more walks of life thinking about this technology and what it might mean for them and their future, and places they might want to invest their time, like you're saying, from a really authentic place. You don't do this because you think you're going to make a bunch of money one day. You do it because it's something you wake up and believe in, like most of us that started our career wherever we started. So,
Thanks.
I'm actually very pessimistic for what's going to happen with quantum technologies in terms of international collaboration. I've been in this field for quite some time, and I've seen, an open and global market, and then some regions gradually closing down to certain technologies and origins of products. And, I think in the next few years, the trend is only going to continue. There's not much we can do, unfortunately. The big countries and the big players will push their way through, and the mice will have to follow and try to find some cracks. So I'm pessimistic. I think what's important at the end of the day is that the scientific collaboration remains. You know, there's business, and then there's a question of technological sovereignty, and there's greed and this kind of things. But what's important is that knowledge requires collaboration, and that at the scientific level, really we can maintain a high level of collaboration. For the business, we'll see.
Yeah, I mean, that's a very interesting, and thank you for sharing that perspective. I don't know if, Microsoft is a multinational company, and you're one of the big gorillas here, so I don't know if you want to speak on behalf of your company, but you're sitting in a position that's got a different point of view, perhaps. Would you share anything from there?
Well, what I was thinking when, hearing both Raj and Gregoire, I think one thing to be aware of when we think about the coming year, and really recognize, right, the pace of innovation, we are accelerating incredibly fast, right? When we look at, AI, right, all the different models coming out and how much more advanced they are month to month, right? This is fast innovation. I can speak for what we've done at Microsoft, right? A year ago, we had 0, what we call reliable or logical qubits. These are qubits that are made from physical qubits, and they should have better performance capabilities than the underlying noisy physical qubits they're built from. And, we started a year ago with Quantinuum, 1 year back, 0. With Quantinuum, we showed the first logical qubits on record that were better than physical. 5 months later, we tripled that number with Quantinuum. Another 2 months later, we doubled it again on atom, with atom computing. So I think this pace of progress it's fast. And I want to mention that in the context of the question on government's International Year of Quantum, what can we do? I do think, one piece of this, we have to think, how do we support that pace of innovation? How do we support that pace of innovation globally? There's everything from, export, right? There's all these policy questions underneath there as well, right? Data sovereignty, export control, immigration and visa, right? How do you hire the right people? Then there's the training, right? So there's a lot that we have to do in addition to the science and technology to support this pace of progress, right? And this pace of innovation. So I think, for this group in particular at UNESCO, right? How do we support that? I don't have a good answer, Gregoire, to your thoughts there.
I do think the last thing I'll add is that I agree with you on the international relations, but I think across our platforms, right, we're all, especially the larger companies and the startups, we are thinking about how we can bring some of the smaller groups along with us, right? How do we open up our platform and allow for other software technologies to be on top, right? IBM has introduced functions and other add-ons and things like that people have ideas, how can they build it on top of the platform? Other companies are also allowing different back-end providers to be on there. So I do think in these stages, most of the companies who are, pioneering are thinking about ways to really build the ecosystem. None of us can do it on our own. We have to find ways to continue to collaborate at the academic level, and as well as allowing people to build on top of the platforms and get those good ideas to our user bases.
Thank you. One more comment?
Yeah, so my own thoughts are that, we're celebrating 100 years of, progress in quantum science and technology, and we're really excited about the rapid pace of innovation that we have seen so far. I think we should just remember that this was possible because we were always operating in a much more open ecosystem. People could flow, ideas could flow. We were sharing information. So I do share Gregoire's concerns about the future. I hope that if there's one thing that we can take away from the year is that we should maintain the scientific collaborations, because I think that's the only thing that will actually sustain the rate of innovation that we are seeing.
I think the reason everybody agrees that collaboration is so critical is fundamentally quantum computer can really accelerate the progress of science itself. So if we can make faster progress, we believe we can contribute to the humanity as a collective. And maybe it's a little bit a humane touch, but one way to make Rigor a little bit more optimistic is if we have more face time like this, I think that goes very far. And I think Professor John Doyle mentioned at the beginning as well that if you are actually meeting with each other and collaborating from a young age in person, then it's likely that this kind of collaboration and friendship actually continue. And I think this is really important in the era of digital media, that we really need to see each other, spend time together, and then I think more optimistic perspective of collaboration will come out. That's my belief. Yeah.
I think we'll end on this upbeat note. I tend to agree with you. I think that government has a responsibility. There are parts of government that are about protecting and making sure that national security interests are protected. But there's the sort of run faster and win, side of things too, that industry is more, interested in a sense. So how to maintain that pace of progress, and that's going to require, as you said, more than one entity, because no one can do it alone. It's a global, there's globally smart people all over the world, there's innovation happening all over the world, and there are markets and companies all over the world. So collaboration, I think, is going to be key. So in the last 15 seconds, I'm going to do a really speed round here at the end. I sort of distilled the last question about, what would be your advice to someone who wants to learn more, because we do have some people in the audience who perhaps are not, well, before today, were not expert. Now that they've heard some great talks, they know more. And so I thought maybe you could just say, if you have a favorite book or even movie or something entertaining that you would recommend to someone, what would it be? And I'll start while you think, because I actually found on a sort of free library the Walter Isaacson Einstein biography. It's not a thin book, it's pretty big, but it actually has a very good description of quantum mechanics in there in telling the biography of Einstein. So it's a fun story and a great, very well written book. So that's one way that I would encourage people who want to know more about quantum to learn about it. So do you have any resources you want to point people to?
The only thing I'd say is if you find a really good book, please let me know so I can read it. No, unfortunately, I don't watch movies, so I can't tell you movies. But given what quantum is going to do, which is essentially a disruptive, but hopefully cooperatively disruptive technology, for us, I'm more on the business side of things, rereading Christensen's book on, the innovator's dilemma is, I feel, a must for everybody who is in the business of this exciting technology.
I mean, this is really hitting on the point that physicists think they can do everything because they're so smart about physics, but business is not always their strong suit. So that's a great suggestion. Thank you.
I think I'll be selfish really quick about IBM. We have excellent educators on John Walters and Olivia Lanes, who have done a phenomenal job on some just really nice videos on quantum information, basics on quantum circuits, how do you apply them, what do you do? And then I was talking to someone else about a book about Marconi and some of the early days of experimentation in wireless, and it was like this, he had this maniacal focus of, I know this is gonna work, I'm gonna use this technology, I'm gonna make it work. And I think anything like that, where people have really battled technology and won, is super fascinating too.
The book that got me into physics was, the book called, You Must Be Kidding, Mr. Feynman. That's a famous one. And I actually, just like Professor Alain Aspect, I actually watch a lot of YouTube video. So, yeah, those are actually good.
Well, I'll go beyond books and say, now with AI, you can turn to your co-pilot and get a good summary. So let me point all of you to our Quantum Copilot, where you can ask it to write a program for you in your natural language. And you can have it then write a program for teleport or entangle or, as you wish, or you can learn more about quantum chemistry there. So I think, in one sense, all of these books are, in some sense at your fingertips. through these Copilot capabilities. So I
Does
encourage you to go there.
do pretty well
at
with
Azure Quantum.
Lots of different languages?
What's that?
Does it work pretty well with lots of different languages?
We have it mostly, yeah, so you can use different languages, but it'll produce Q# code, which is the programming language we've developed for high-level quantum programming.
Right, so I wouldn't go with a book. I would say that, again, there's lots of material out there. You look at a lot of the quantum centers around the world, including our own in Singapore. We have a YouTube channel. We have the Q-Talent platform. Just go online and look. Important thing is get it from a trusted source, right? And just dive in. You'll find lots of interesting information out there. Very inspirational often.
There's a great book here more about the cryptography side, the book by Simon Singh, The Code Book, which presents a historical perspective on cryptography, starting with Caesar cipher, going all the way to RSA and QKD. It's quite old, it's 20 years old, so PQC is not mentioned in there, but it's an amazing book. And actually, I was thinking, Simon Singh is such a great author that I wish he wrote a book on quantum, because that would be an amazing tool for all of us to make quantum more accessible.
There's a tip for him. So thank you all. We ran over just a few minutes, but I'll just wrap up by saying that in my opinion, IYQ can raise awareness. It can raise awareness among customers. Those customers may be government customers, scientific customers, researchers, NGOs, or other businesses, and of course among educators and students and all around the world. So I want to thank this fantastic panel, and I look forward to the rest of the conference. So thank you very much.